In this video, we're going to consider proof by induction. And proof by induction is a method we can use to demonstrate that a mathematical result is true. Anytime you see a mathematical result, that result has been proven to be true. Someone's demonstrated that that result is in fact true. And proof by induction is one of the ways, but not the only way, we can use to demonstrate that a result is indeed true. So we're going to work this example in a moment. We're going to prove this result is true using proof by induction. And proof by induction works really well for scenarios with summation, sigmas, series, infinite series, or basically when you've got a unknown or an infinite number of cases to prove to be true. Proof by induction, in terms of the method, works as a two-step process. So the first step is often called the basic step. And in the basic step, we're proving the result is true for the first case. So we're proving this result is true for, in this scenario, where n is 1. And normally that basic step is very straightforward, usually trivial, in fact. The more challenging part, especially if you're new to this method, will be the inductive step. And in the inductive step, we're trying to prove that the result is true for some n equals k plus 1, but only if it's true for n equals k. Or to put that the other way, to prove that if it's true for n equals k, that implies that it's true for n equals k plus 1. And what that means is, if you take some general case, the kth case, then that automatically implies it's true for the k plus 1th case. And this process is often likened to toppling dominoes. If you've got dominoes lined up and you know they're definitely lined up, if you topple that first domino, it will just hit the second one, and the third, and the fourth, and they'll all basically follow. So this is like proving that your dominoes are lined up, the inductive step, and the basic step is like toppling over that first domino. So we're going to work this example in a moment. Before we work this example, let's just think about what this example actually means. These proof by induction methods can be used on any type of proof. This one happens to be to do with a series. This is saying that if you take the sum from r equals 1 to n of r, the result comes out to be 1/2 n times n plus 1. So for example, if we let n equal some actual value, so if we let n equal 5, say, then that's going to be the sum from r equals 1 to 5 of r. Remember, this r in here is just a placeholder. It's just telling you what to do with the numbers. In this case, we're just taking the numbers and adding them together. So that would be 1 plus 2 plus 3 plus 4 plus 5. And that is 3, 6, 10. That comes out to be 15. Now that was actually quite straightforward to do. But imagine if that r value, that n value, sorry, became 10. Or 20, or 100, or 1,000, or 1,000,000, it would become cumbersome to make this calculation. This formula says, well, you don't need to do the calculation, you can just put your n value in here and work out what you get. So let's just test that that does actually work. So if we take 1/2, this time we're changing our n to 5, so 1/2 times 5 times 5 plus 1. So that's going to be equal to 1/2 times 5, 5 plus 1 is 6, so times 6. 1/2 times 6 is 3, 3 times 5 is indeed 15. So that comes out to be the same result. So that's just a demonstration of what this result in this case actually means. Now we want to go ahead and use proof by induction to show that this actual formula, the original formula we've just used there, is indeed true. So always remember, when you're doing proof by induction, you've got to go through the two steps. So we're going to start with the basic step, which is, like I say, normally fairly trivial. So in the basic step, we're trying to prove the result is true for the first case. The first case in this example is when n is 1. So you're basically letting your n equal 1. So that would be the sum from r equals 1 to 1 of r. But that's just one term. That's just that first term. So that is just equal to 1. And you're done, right? That's just the first term. We want to prove that that is true for the formula. So we're going to work the sigma. We've worked the sigma part on this side, we're going to work the other side of the formula over here. We're just letting the n value be 1, so it's going to be 1/2 times 1 times 1 plus 1. So we're just plugging 1 in the place of the n in the formula, just like we did here with the 5. 1/2 times 1 is 1/2. 1 plus 1 is 2, so it's going to be 1/2 times 2, which equals 1. So these have come out to be the same value. So that means that we can sort of validate, sign off on the basic step being true. The basic step is usually quite a small amount of working. I want to move on and have a go at the inductive step, which is definitely more challenging. And at first, the inductive step, if you've not seen proof by induction before, it will seem weird, right? It will just take a while to get used to it. The important thing here is that we're going to assume this result is true, which means that at some point in our working, we'll need to pull in or use that assumption, but we're trying to prove that it's true for the next case. What this actually means in practice is that our assumption is that when n is equal to k, the result is true. So if you change the n to a k, then our assumption is going to be like this. So we're allowed to assume that the sum from r equals 1 to k of r is equal to 1/2 k plus 1. So notice that that is just the result we had already, but changing the n's to a k, and that's a result that at some point we need to use in our working. But what we're trying to show is that this implies that if that is true, this implies that the result is true for k plus 1. In other words, r equals 1, the sum r equals 1 to k plus 1 of r is going to be equal to 1/2 k plus 1, k plus 1 plus 1. So it'll be 1/2, changing the k to a k plus 1, changing this k to a k plus 1, so it'll be k plus 1 plus 1, which is k plus 2. So that's the result we're trying to show to be true. Now this that I've written down here, this here is not part of our working, it's kind of side working. You wouldn't need that as part of your answer. It's just to kind of guide you along, because it's easy to get lost in the algebra in these questions. So this is what we're trying to show to be true. So let's start with this here, this left-hand side. So it's going to be the sum from r equals 1 to k plus 1 of r. And these questions where you're using proof by induction, they don't have to be about infinite series or finite series. They can be about anything, but if it is a case where it's to do with a series, which a lot of them are, it's a common trick to split your series as the sum from r equals 1 to k. In fact, it's not a trick, it's something you've got to do. So it's r equals 1 to k of r. And so that would give us the terms all the way from 1 right up to k. We've got k plus 1 terms, so we've only got one more term, and it's the final term, it's the k plus 1th term. So I'm just going to write this in. You wouldn't normally write this in, but just for demonstration, the thing we're going to add to this is the k plus 1th term. The final term, if you like, in the series. A little bit like splitting the sum from 1 to 5 as a sum from 1 to 4, and then adding on the 5th term, which would be 5 in that case. So what does that k plus 1th term look like? Well, it's just r replaced with k plus 1 in this particular case. So that's going to be the sum from r equals 1 to k of r plus k plus 1. But this part here, the sum from r equals 1 to k of r, is the thing that we are allowed to use as our assumption. This is where we're going to pull in that result. So this part here we know to be just 1/2 k plus 1. That's for this bit. K plus 1 on the end is just going to stay there, k plus 1. Keep an eye on where you're trying to get to. We're trying to get to this here. So there's always a little bit of algebra in these questions, and it's not always easy. It might take a bit of experience. But notice here there's a common factor of k plus 1. So you could start by pulling out the common factor. There's different ways you could finish this question off. If you pull out that common factor, if we then use a bracket, we would need a 1/2 k for our first term, and we would need a 1 for the second term. So k plus 1 times that gives you that. K plus 1 times 1 gives you that. So that's a factorising complete. Notice that in the final answer, they've got a 1/2 in front. So what I'm going to do, I'm going to keep my k plus 1 term, because there is a k plus 1 term in the final answer. But what I'm going to do is introduce a common factor here of 1/2, which would then look like this. Now this might look a little weird, and like where did that come from? But if you think about it, 1/2 times k is 1/2 k, 1/2 times 2 is 1. So I've just rewritten the 1/2 k plus 1 like this. But the reason why I've wanted to do that, that now introduces the terms that we need in our proof. So just by reordering those, that'll be 1/2 times k plus 1 times k plus 2. So down here we proved that the basic step was true, that trivial step. Here we've now proven that the inductive step is true. So that completes the proof. So now we can say that that result is indeed true. This whole inductive step will be tricky at first. And my main advice to you would be to understand the method, first of all, what you're trying to achieve, but also just to work a bunch of examples. It's definitely something that you need to do rather than just sort of theorizing about. It is quite useful to write down what it is you're trying to assume, or what it is you're going to assume, and what it is you're trying to show, because this gives you an end goal. That's where you're trying to get to. You're trying to get from here to here. So we started there, the left-hand side, and we developed it into the right-hand side. But the important thing is at some point, you'll need to use your assumption. That's our assumption there. That's what we pulled in from over here. So that's how we proved that result using proof by induction.